Bandyopadhyay. He's a postdoc at the Systems Medicine Department at DZNE, led by Schultze. He will present the Liberate AI project, funded under the Helmholtz AI call, I think. There's a collaborative initiative involving DZNE, the University Clinic in Bonn, and CISPA. And this project aims to develop an AI tool using a decentralized approach, swarm learning, to analyze MRI data from the German Stroke Registry. And really looking forward to your talk.
Thank you for your kind words, and good morning, everybody. Liberate AI deals with the problem of any emergency department of any stroke unit of university hospitals. So, ischemic stroke is one of the leading cause for the mortality and disability. And for most of the patients, it happens when there is a clot in the blood vessels and the tissues do not have enough oxygen, and the tissues become necrosis within a few minutes. And most of the patients, when they reach to the emergency department, what happens is that substantial amount of the time they have already spent before they reach to the emergency department. And then the clinical variables have been measured, the imaging happens, so that also takes quite some time, and therefore there is a substantial amount of the time has already been spent. And there is the important point of the treatment here is to have this golden hour after the stroke, that we do not know when the stroke onset has happened, and there is a substantial amount of the time that's been passed. And that's in terms of the treatment, there are intravenous thrombolysis, but that also depends when the patient reaches to the emergency department, and there are other, like the mechanical thrombectomy, where the blood clots are removed mechanically by the clinicians. Now, for most of the patients, this treatment is not effective. We'll show in the data that more than 50% of the patients, this is not actually helping them. And also, as we don't know the onset of the time, that is really having the pressure on the clinicians at how they will deal with that. So this is, and also this treatment is not a risk-free. There is complications like intercanalical hemorrhages and many other complications that might happen. So this is where the Liberate AI comes in, and we took up, and we think that with the deep learning model, with the clinical variables, and as well as with the imaging, we can try to understand that for which patients the treatment occurs, and for which treatments this treatment benefits, and so that we can minimize the risk of the complications. And I hope that in the future that will reduce some social burden. So for that, we are using German Stroke Registry, which is an academic observational multi-center registry where more than 25 university hospitals data are enrolled. The inclusion criteria is that all the patients are adult. They have the strokes, of course, and they have a large vessel occlusions, and there is an attempted endovascular treatments. And for most of the patients, they have the CT images, but there are limited MRIs. For this work, we are considering the MRIs at this moment. And MRS 0 to 2 is considered to be acceptable outcome, where the patient can manage their daily work by their own. The MRS score is 3 to 6, is that somewhat the patient is dependent to the other people for doing their daily task. So this is unacceptable outcome. There are several clinical variables that have been measured by the clinicians. For example, NIH score, 24-hour MRS score, and diabetes, and the medications they took, and what are the treatment that is happening. Many other clinical variables, for example, aspect score, etc. And here we are predicting the 90-day MRS score. And for the benchmarking purposes, when there are many studies around that. For example, when they have used only the imaging, they have the accuracy of 70%, and the AUC is approximately 75%. But when they use only the clinical informations, the accuracy is 65%, and the AUC is 70%. When they use together imaging and the clinical informations, they reach to the same values to the imaging facilities. So these are important for the imaging purposes. So we have several imaging modalities like DWI, FLAIR, T1 and T2 sequences. As you can see, the DWI is the best in this context, DWI and FLAIR. For both of the cases, the stroke is very much visible from the early time points, and as the time progresses, it's much more visible. In this work, we are using the FLAIR sequences. Now, there are two important investigation direction in this work. One is the subgroup discovery, and another part is imaging. Professor Vreeken has already spoke quite amount on the subgroup discovery the other day. He has also introduced the SciFlow, which has been used. So in summary, what it does is that it tries to found a subgroup within the populations for which the outcome is significantly different compared to the other populations. For example, in here, we are using 35 different features and more than 8,000 patients in here, and we are trying to predict for which the 90-day outcome is significantly different compared to the population mean. And here you can see in the green that the subgroup has been found, and the population is been shown with these gray bars. And we found that approximately 1,000 patients, this distribution is significantly different. For example, NIH's score is around 10. That means the moderate stroke, not the severe stroke. Pre-stroke MRS is 1.59. That means that the person, before the stroke happens, there is some level of immobility there. So what we conclude from here is that if the patient has already some immobilities and the mild stroke happens, then that patients are the risk group. So clinicians may consider that for consideration. And then the imaging part, I will not go with this pre-processing step because this is not very interesting in here. So what we are trying to do here is the binary classification. 0 to 2 is acceptable outcome, and 3 to 6 is unacceptable outcome. We are trying to predict the 90-day MRIs. So far, we have approximately 280 MRI images coming from the different centers. We are considering at this moment 10 different centers, but for this work, we have only 4 at this moment. And you can see it here in the second plot in here, that more than 50% of the patient, the outcome is not good, and this is consistent for across different centers. And in here, we can also see that that the percentage of the bad outcome is bad, and there is also class imbalances, but probably that is not severe in our case. And then we are trying to the 3 different model training in here for ResNet 34 depth unit and swing transformer. Among these models, ResNet model performs poor. As you can see from the confusion matrix, that the accuracy is approximately 60%. AUC curve is also 63%. The unit and swing transformer performs better, where it is approximately 70%, and the accuracy reached the 73%. And also, it's very important here to keep in mind that in our data sets, there are several sources of heterogeneity because it's a multi-source, multi-scanner, and the thickness level of the MRI is very different because it's an emergency conditions taken up. So there are several layers of complexity in here as well as the batch effects. Yeah, and then we tried different classifier to improve from the embeddings to upscale the performance. So in here, we tried several classifiers that didn't work out, but what worked out is a stacking methods where we have several, with the embeddings, we have the base models, and then we concatenate the probabilities, and there is a meta model that is then classifying between these 2 classes. And what we see that the accuracies drop slightly to the 71%, and the AUC reached to the 77%. So we see that there is the similar performance that you see in previously found literature. So in summary, what we have so far have found some subgroups that are interesting as well as some imaging things, and we would like to integrate these 2 methods in order to better classify for these patients. For example, the 1,000 patients that we have found that have significantly different, we can investigate those further. At this moment, we have centralized model training methods, but in the future, we would like to do decentralized methods, so the data remains wherever it is. we will apply the data visiting principle using the swarm learning methods, where there is no leader for communicating, and all the communications happens through the permission blockchain, and that is very secure. So this is fully decentralized, democratic, and in compliance with the FAIR principles. So with that, I thank you, our department, the Delivered AI team. It's a collaboration between the CISPA, Vascular Neurology Department, and DZNE, all the other CISPA departments, and Helmholtz Schultze from the HPE to provide the technology, funding agencies, Helmholtz AI, and in-kind contributions of the DZNE, UKB, and CISPA. And thank you for your attention. I'm happy to take any questions you may have.
We have time for questions. There's one.
How did you define the initial subgrouping based on the clinical information?
So we have the 90-day outcome patients. So this SciFlow already, so there is no initial, we don't need to tell anything about this method. So if we give that this is our outcome here, we are looking at 90-day, that will automatically find the rules. So for example, we initially considered 35 different variables, which is the most important from the clinician. So this comes from the clinician's feedback, and we restrict to this this big data matrix is considered the 35 variables and one outcome, and then the methods automatically finds out what are the conditions for which the distribution is significantly different compared to the population.
Thanks.
All right, let's thank Arnab again.
Thank you.